Welcome to Pop Culture 101 channel. Day in the first episode of our series, analyzing time travel from movies' perspective. Time travel in cinema, relativity, loops, and the Tesseract. Cinema often explores time travel through two broad paradigms. One is a closed loop or circular timeline, where the past, present, and future form a self-consistent cycle. This predestination or Bootstrap Paradox occurs when an event in the future is the cause of an event in the past. In fiction, this leads to mind-bending scenarios who wrote the original message, where an effect is its own cause. The other paradigm is a dynamic, linear timeline, mutable timeline, where characters can change history or branch into alternate futures. In this view, time is more like a flowing river or highway, and actions can ripple forward or even create new timelines. Many time travel stories hinge on one of these approaches, often invoking Einstein's theories of relativity and concepts from quantum mechanics to ground the fantasy in science. For instance, wormholes, Einstein-Rosen bridges, are popularly imagined as cosmic tunnels through space or time. And some theoretical work suggests exotic time symmetry in quantum physics. In modern physics, special and general relativity rigorously predict how time behaves at high speeds or strong gravity, while quantum theory opens the door to ideas like entanglement, multiverses, or time-symmetric processes. As we'll see, Interstellar uniquely blends these concepts. It treats time as a literal navigable dimension inside its climactic tesseract, and its story embodies a circular loop paradox so that cause and effect form a circle. The Interstellar framework, Cooper's journey into the Tesseract. Interstellar is set in a near-future Earth in crisis, where NASA has secretly discovered a wormhole near Saturn leading to a distant galaxy. Former pilot Joseph Cooper Matthew McConaughey leads a mission through the wormhole to find new habitable planets. After exploring several worlds, Cooper ultimately sacrifices himself by plunging into a supermassive black hole, Gargantua, to save his crew. Instead of dying, he finds himself inside an extra-dimensional structure called the Tesseract. This is an unusual tesseract where time is a physical dimension. Inside, Cooper simultaneously perceives his daughter Murph's bedroom at many different times. The Tesseract was created by advanced beings implied to be evolved future humans to allow Cooper to interact across time. Kip Thorne explains that this five-dimensional construct is a piece of advanced technology that lets Cooper transmit quantum data from the black hole singularity to Murph in the past. Inside the Tesseract, time is laid out as space. Cooper sees the world tubes of familiar objects, paths through space-time that look like four-dimensional tubes, each slice of which is the 3D object at one instant. In this surreal space, Cooper can reach out and push on these world lines. For example, he touches the world tube of a book and of his wristwatch. When he does so, he generates a gravitational wave that travels through the Tesseract's higher dimensional bulk. Crucially, this signal travels backward in Murph's time, even as it moves forward in the Tesseract's local time. In practice, Cooper uses this to communicate. He taps on his watch's second hand in Morse code, encoding the data about Gargantua's interior that he recovered the quantum data necessary to solve NASA's gravity equation. The Tesseract stores the twitching pattern so that it repeats over and over. Decades later, a grown-up Murph, Jessica Chastain, discovers her father's old watch and finds the second hand inexplicably twitches in a steady Morse sequence. This loop of information, Cooper's future self sending data to his younger daughter, directly saves humanity by letting Murph complete the equation for gravity and launch the evacuation of Earth. The physics breakdown, relativity and time, special relativity, high-speed time dilation. Einstein's special relativity 1905 revolutionized our understanding of time and space at high velocities. It predicts time dilation. A moving clock runs slower relative to a stationary observer. In other words, time literally slows down for objects moving near light speed. As Space.com explains, an object in motion experiences time dilation, meaning that when an object is moving very fast, it experiences time more slowly than when it is at rest. A classic example: a teenager traveling in a spacecraft at 99.5% of light speed for 5 years would personally age 5 years, while on Earth, over 50 years would pass. In that scenario, upon return, she might meet grandchildren who have already lived a lifetime. We see a glimpse of this in Interstellar. Visiting Miller's planet near Gargantua incurs such intense time dilation that 1 hour on Miller's equals 7 Earth years. Thus, after a short mission there, the crew learns that 23 years have elapsed for Romilly back on the Endurance. Special relativity is also the principle behind the twin paradox. The traveling twin ages far less than the earthbound twin. Today, this effect is confirmed in particle accelerators and even GPS satellites, which must account for it. In short, nearing light speed stretches out your personal time relative to the outside world. General relativity, gravity, and time. Einstein's general relativity 1915 further teaches that gravity itself affects time. Massive bodies like planets or black holes warp space-time so that clocks in stronger gravitational fields tick slower. In the film, Gargantua's titanic gravity drastically dilates time on Miller's planet. NASA illustrates this idea. Time passes slower closer to the black hole than further away. In other words, if you hover near a black hole's event horizon, 1 hour for you could be years on Earth, even on Earth. We experience tiny versions of this effect. Clocks on high-altitude planes tick a bit faster than on the ground due to weaker gravity. Astronauts on the International Space Station age microseconds more per year, relative to people on Earth because they are farther from Earth's mass. But near Gargantua, the effect is enormous. After Cooper's slingshot past Gargantua, his crewmate Romilly ages decades, while only hours passed for them near the planet. This gravitational time dilation is exactly what general relativity predicts. Space-time and the fourth dimension. Relativity unifies space and time into a four-dimensional continuum. In everyday life, we move through 3 spatial dimensions: length, width, height. Relativity says time is the 4th dimension, an inseparable part of the fabric of the universe. NASA succinctly describes space-time as a 4-dimensional description of the universe, including height, width, length, and time. In other words, time is a dimension much like the others, though we normally experience it only forward. In Interstellar, Cooper's journey into the Tesseract essentially upgrades him from a 3D being to a 4D navigator. Instead of living along a single world line, he perceives a stretch of space-time at once. He can move up and down through time as if it were space. Conceptually, if we imagine treating time as another accessible direction, we become 4-dimensional entities moving through a space-time block. Inside the Tesseract, this abstraction is literal. Cooper watches slices of Murph's room at different years and physically moves between them. It is like watching a 3D movie looped on a 4D projector. The physics of the film connects to this. Cooper sees the entire world line path through space-time of objects. Thorne describes these as world tubes, a sort of 4D tube for each object's history. Pushing on these tubes, like pushing on the second-hand world tube, sends ripples in space-time backward in Murph's time. In essence, navigating time freely in the Tesseract treats Cooper as a 4-dimensional being. This is beyond our real physics, but relativity does allow us to conceive of space-time as a 4D landscape. The eternal loop, the Bootstrap Paradox. The climax of Interstellar is also its most paradoxical. The Bootstrap causal loop paradox is fully realized. Cooper's actions in the Tesseract ensure events that led him into the Tesseract in the first place. In practical terms, Murph only knew the NASA coordinates to the secret station because Cooper sent them via the books and watch. But Cooper only ended up at that station because he found those same coordinates. The future created the past, which created the future, a perfect time loop. As Wikipedia notes, such loops are also called a predestination paradox, or ontological paradox, or bootstrap paradox. In one moment, Murph even deduces this herself. She realizes the supernatural coincidence that led Cooper to NASA was Cooper himself communicating from the future. In her watch came from her father's future self, which was sent because of events she herself set in motion. This is like a ring of dominoes. The last domino falling triggers the first. If any piece were missing, the whole chain breaks. The film suggests the timeline is self-sustaining. The very origin of the wormhole and Tesseract is tied to Cooper's journey, and vice versa. As writer Justin Alexander explains, in Interstellar, all of time exists simultaneously inside the Tesseract, radically altering causality. While this defies our usual linear sense of cause and effect, it is consistent internally. It's a closed loop where Murph's childhood discovery of the watch leads her to solve the equation and launch humanity's exodus. All because future Cooper sent that data through time. The trigger of the loop is blurred. Cooper goes because of coordinates his older daughter found, and she finds them because Cooper went. Hence, the narrative becomes a circle, a bootstrap paradox. In summary, Interstellar frames time travel not as altering history, but fulfilling it. Past, present, and future are interlocked. This loop underscores a key theme: love and human connection transcending time. But scientifically, it highlights the weirdness of time as a dimension. From a physics viewpoint, it assumes Novikov's self-consistency. Whatever happens in the loop was always meant to happen. Whether one accepts it or not, it's a striking example of circular time travel in modern sci-fi. In the end, Interstellar weaves complex physics and paradox into a memorable cinematic tapestry. We've seen how Einstein's relativity gives shape to its story, slowing time at high speed or strong gravity, and how the film imagines a fourth dimension of time itself inside the Tesseract. We've examined the bootstrap paradox that makes the film's timeline one unbreakable loop. All these concepts are grounded in real science, with help from physicist Kip Thorne, yet they're pushed to creative extremes. And if you enjoyed this deep dive into time travel and interstellar and cinema, make sure to subscribe for more science and pop culture breakdowns. Hit that bell icon so you don't miss our next video on the physics of your favorite movies.